Log on, tune in, find out. Another good idea from Cambridge.
An important place, and to spend here, I believe, fruitful scientific period of my sabbatical. So let me start my talk dedicated to what is written here, to some applications of ideas borrowed from the modern theory of completely integrable systems and dedicated to some new approach to the discretization of complex analysis. So just let me start from the beginning that, of course, discretization of complex analysis is not a new subject, as I am doing it, as I am not the first person who started to do this. My approach to this problem has nothing to do with geometrical discretization based on the geometry of conformal maps. It was started by, I believe, by Kirby himself in early 20th century. It just continued later by several people, including Thurston, but has nothing to do with our stuff. I'm going to consider discretization of complex analysis as a theory of linear operator, of Cauchy-Riemann linear operator. It's also not the first approach to that. And let me just start with introduction in theory of completely integrable systems, which ideas I borrowed for this new approach. That's a famous discovery of Martin Kruskal with company of the so-called inverse scattering transform, just generated what we call today theory of completely integrable systems. Thus, of course, you should not think that that completely integrable systems also never has been considered. Completely integrability in mathematics of differential equations, I think first discovery was done by Sir Isaac Newton himself, also famous systems of that type, yes. Also, even in 19th century, theory of Riemann surfaces started by Jacobi. Also, at least half of its sources was discovery of new completely integrable systems where symmetry, group symmetry was not obvious. But the inverse scattering transform, which is a starting point of big part of modern ideas in mathematical physics, and which made influence on in all development of today's effective methods of analysis. It started from famous work of a group of, say, somehow applied mathematicians or plasma physicists, whose head was Martin Kruskal in mid-60s. And it's called inverse scattering transform. That's between mathematicians who immediately joined this area. Peter Lux also played fundamental role. The question is following: how to solve the so-called KdV equation? It's 19th century equation. Soliton was discovered even before. I think Rayleigh himself found solitons, Boussinesq, some 19th century famous scientists. Korteweg de Vries produced equation for shallow water problems. In plasma physics of 1950s, it was somehow observed that these KdV equations might appear in many problems of describing in some sort of first approximation some waves, nonlinear waves in dispersive media. Many different kinds of waves, in particular in plasma physics. But it is nonlinear equations. It appeared already in 19th century. That's how to solve it. And especially for the so-called soliton type profiles. When you consider rapidly decreasing initial values, u is normally velocity in hydrodynamics. It's after some just small changes, equations can be reduced to form with coefficients which I wrote above. And this, some numerics also played role here. Soliton interactions was discovered numerically, showing that this equation is quite unusual, no matter that it appeared already in 19th century. In 1967, in famous work, Gardner, Green, Kruskal, and Miura discovered this so-called inverse scattering procedure. Remarkable procedure involved, it's non-trivial integrability, not just substitution of functions of elementary substitution like that for complete integrability. It's a global procedure depending on boundary conditions and so on. For rapidly decreasing initial profiles only. Depends on modern quantum direct and inverse scattering problems. Let me avoid mathematical structure of this procedure itself, so-called inverse scattering procedure. Just let me mention that mathematical byproduct of that was analyzed by Peter Lux, who, I would say, revealed algebraic reason why this procedure is successfully works for that. And he also produced some first generalizations of that systems. And some important development started soon, not immediately, but soon. But just, of course, a lot of people in physics, especially in physics community, was highly surprised by this strange, unexpected procedure for this equation. It is physically meaningful equation, but of course the beauty and the role of this discovery in development of mathematics, different area of mathematics, is much higher than its role in describing purely physical nonlinear phenomena. Some other systems were found soon, few years later, not immediately, but soon, where such procedure also works. And between these systems, there are some systems also known since 19th century, geometry, like Sine-Gordon, two-dimensional Toda lattice, and so on. It's a lot of systems. Some of them appeared in different branches of physics, like nonlinear optics, and so on. That's Hamiltonian treatment started also soon. I myself started to work in this area in 1974. That's because for periodic boundary conditions, this procedure in its original form did not work. So it took years to solve periodic problems after rapidly decreasing. I told you that it is not substitution, an elementary set of substitution. It highly depends on boundary conditions. So in particular, if a solution for for soliton profiles, rapidly decreasing Cauchy data led to inverse scattering procedure, the periodic case led to theory of Riemann surfaces, use of theta functions. Riemann surfaces later improved theory of theta functions themselves as well a lot, used in algebraic geometry itself and theory of theta functions. Also highly improved theory of fundamental linear operators, like periodic linear Schrödinger operators, understanding of them, and unification of that theory with algebraic geometry of Riemann surfaces was also important step, in my opinion. So my personal point of view in that, I'm working in that area since 1973, approximately. And my point of view is following, that this completely integrable system solvable by inverse scattering transform are something exotic. In some cases, they are important. Good systems like KDV or St. Gordon or two-dimensional Toda lattice appeared in many problems, including from geometry to quantum field theory. But still, it is something, I would say, relatively small collection of highly exotic, very beautiful systems. It's strange that they appear in different problems. But from our side, if looking this from our side, one might observe that these nonlinear systems can be naturally considered as some sort of new type of symmetry for some very fundamental linear operators, like which you meet everywhere, like 1- and 2-dimensional Schrödinger operators, for example, with some fundamental boundary conditions like scattering type boundary conditions like in quantum physics, or periodic boundary conditions like in quantum solid state physics, for example, and so on, with translation invariant fundamental boundary conditions. And this exotic symmetry discovered after this inverse scattering transform might be really useful to improve, in particular, spectral theory of very fundamental linear operators, especially in 1- and 2-dimensional case, not 3-dimensional case. 1 and 2, even not only in 1-dimensional case, but also in 2-dimensional case. That's inverse scattering transform basically does not touch 3-dimensional system. There are 2-dimensional case, several very interesting fundamental examples, but not 3. We shall discuss it later. 1-dimensional Schrödinger operator, 2-dimensional Schrödinger operator, parabolic operator also means 2-dimensional stuff. Dirac operator, some matrix operators, but also a lot of these fundamental, very fundamental linear operators are associated with inverse scattering transform. Inverse scattering transform is really depends on boundary conditions. It's not local classical type procedure. It's something completely new. End of 20th century, last quarter of 20th century. In particular, for example, famous Pinlevé equations appeared in process of applications of that technique to the famous problems of the so-called random matrices. This also are treated today using inverse scattering transform, but boundary conditions are beyond periodic and rapidly decreasing. So therefore, this theory is very complicated, at least, and much less effective until now. Maybe study important future activity. Let me just present you elementary idea for which classes of operators such symmetry exists. Let me present it in very simple form. Just forget about complicated algebraic geometry or inverse scattering borrowed from quantum mechanics or Hamiltonian dynamical systems. Just elementary algebra of operators. It turns out, I think I'm not sure that 100% of experts will agree with me, but serious part of them will, that one of most important properties of linear operators, which somehow is just lies in core of this symmetry, which we call symmetry, existence of non-trivial, nonlinear systems like KdV type associated with given linear operators, is simple property of factorizability of that operator. Like presentation of operator into form of product of some operators of smaller order, like that. Or something like that, plus constant, or sometimes in two-dimensional case, instead of constant, maybe plus scalar potential, or something like that. Something, in simplest case, just factorization up to constant. Simple factorization. Let me remind you that one of most fundamental properties of one-dimensional Schrödinger operator is discovered, in fact, by Euler in 1742, is that it is second-order operator. Like second-order polynomial, it can be decomposed in product of two first-order operators. Euler did not wrote this, as I am saying you now. This form is given only after late 1940s, when Dirac, Schrödinger, and Infeld, quantum mechanical people started to write operator formalism. Always use operator algebra working with operators. In that case, so Schrödinger and Dirac Infeld wrote even works about that stuff. But I'm just saying you now in this area. In order to decompose Schrödinger operator into this product, you have to solve Riccati equation. Let's try to compare right and left side of equation. You are coming to Riccati equation. It's very simple. Let's say exercise is just in calculus exercise. That's nice to perform it, just one line exercise. Why it is associated with what we call isospectral deformations of operators and so on? Just let me give you a simple example. There is some difference between polynomials and operators. Operators here do not commute with each other. The factors do not commute with each other.
Excuse me, Sergey, can I help you with that?
Yes, excuse me. I apologize.
If I put it on here, is that okay?
Yes, but yes, thank you. These factors, they do not commute with each other. First of all, let me tell you, as I already mentioned, you have to solve Riccati equations for that. So it means that it is not unique. With decomposition, you have one parametric family of them. You have to solve Riccati equation for that. And second difference. So therefore, such decomposition is not unique. But second is following, that these factors, they are, in this case, they are even adjoint operators to each other, formally adjoint. It's good to have this in some important cases, but you can interchange them, that you get different operator, if you will simply permute them. It is different operator, but it has almost same spectrum, practically same. By the way, a famous example of quantum oscillator, which was, according to Dirac, base of whole quantum theory of bosons. It shows that after interchange, one eigenfunction might be lost, just like that. So they have almost same spectral theory of in Hilbert space L2, almost. Sometimes one eigenfunction might be added or lost. Yes, something like almost. So you see, immediately you are coming to the so-called isospectral or almost isospectral transformation. It's not, by the way, without saying any words about operators, decomposition, so on, this transformation was constructed by Euler, as I told you, in 1742. Rediscovered 100 years later by people, so you have different names here after Euler. But already in late 18th century, Laplace used two-dimensional generalization of that for two-dimensional cases, so that certainly it could not be Darboux if it already was generalized in late 18th century by Laplace for two-dimensional case. So you see something like isospectral transformation, which is a base of so-called Darboux-Backlund transformation, reflection for transformations for over nonlinear systems, independently geometers like Bianchi discovered this for negative curvature geometry, and Sophus-Lee transferred it in terminology of purely differential equation theory of Stein-Gordon equations. So there was also, Backlund was some graduate student who made order out of that. It was not his discovery. His name here is something like that. It was basically done by Bianchi and Sophus-Lee for Stein-Gordon. Backlund was some their student who wrote his PhD about that, some ordering that stuff. So for two-dimensional case, there is a notion of weak factorization, something like that. And for two-dimensional case, it already, this presentation, I write here complex adjoint operator d and d bar, but of course, 18th century people like Laplace wrote d by dx and d by dy, just real hyperbolic operators. They intended to improve or construct exact solutions of second-order linear equations. Instead of d was d by dx, instead of d bar was d by dy hyperbolic. But I applied this in my works with Sasha Veselov to spectral theory of elliptic operators, so where global problems are important, so I prefer to write d and d bar, and not dx and dy. But this corresponding analogs of Backlund transformations, or Euler-Darboux-Backlund transformation here is associated with one level only, because W here is function, potential, not constant, so we call it weak factorization. It's interesting that two-dimensional case, only spectral theory of one energy level is involved in theory of solitons. You should not think like standard people doing spectral theory that one energy level is something trivial. In fundamental boundary problems for scattering theory in quantum mechanics or in quantum solid state physics, spectral theory in n-dimensional space is discovered by n-dimensional manifold of eigenfunctions. So therefore, one level is only so-called Fermi surface. It is big. It's very important when in two-dimensional case it is one-dimensional surface which became Riemann surface after complex continuation. Nothing like that exists for three-dimensional case also. So this factorization and its algebraic corollaries is just something which allows to construct non-trivial soliton systems integrable by inverse scattering transform and apply this stuff to improvement of spectral theory, fundamental spectral theory of some very important one- and two-dimensional linear operators, important in quantum mechanics, for example. Let me point out now subject of my talk. So let me point out to you that Laplace operator, why two-dimensional complex analysis exists. There are two reasons for that. One of them is existence of complex multiplication, numbers, yes? as I always, I'm telling in all my talks that it was complex multiplication was discovered simultaneously with negative numbers in same works. But negative numbers was accepted by mathematical humanity immediately, and struggle for accepting complex numbers lasted 400 years. Great Russian mathematician Kolmogorov hated complex numbers, exterminated them in high school education as well as in, for example, it was impossible to teach theory of Fourier series where Kolmogorov was great. Always only sines and cosines. The formulas were stupidly long. I could not understand them as a student. And my friend, geometer Boltiansky, a topologist, told he was corresponding member of Pedagogical Academy. He told me how he got invitation once. He heard that Kolmogorov exactly is going to exterminate complex number from high school education. How he told me how it was. Very interesting. So you see, till late 20th century, some great mathematicians believe that Kolmogorov is really genius mathematicians, but so a little bit, I would say, there were some strange points in mind. Well, what still did not want to accept complex number. Or maybe it is Russian sickness. There was also very good, maybe not as good as Kolmogorov, but also very good Russian mathematician of 19th century, Chebyshev. Yes, he always exterminated complex numbers. That's completely. But it was, Chebyshev was great, but provincial. Kolmogorov was leader of world mathematics. That's different, yes. So maybe it was Russian sickness, I don't know. Chebyshev and Kolmogorov did not accept complex numbers. This is complex multiplication is first reason, but there is second reason for that. This is our stuff, that Laplace operator in two-dimensional case is factorizable through product of d and d bar. And this is our stuff. It's associated with theory of completely integrable systems. We are going to construct new discretization of Laplace of complex analysis, ignoring multiplication. Let me tell you that discretization of complex analysis always avoid multiplication. My discretization, my new discretization, as well as classical one made since 1940. I will tell about that a little bit. All multiplication should be lost. That's no doubt in all approaches. Believe me, if it would be possible to preserve multiplication, holomorphic functions after discretization, it would be known at least 150 years already. Yes, but it's impossible. Now just let me say a couple of words about discretization. Even in one-dimensional case, Soliton theory taught us something. Even in one-dimensional case. Let us consider shift operator, elementary shift operator on the just real line, just Z, simplest discrete case. In order to preserve factorization property, and you should not use standard discretization, which all computational mathematicians used long before. What is written in my transparency is discretization of second order operator. This is, and in standard classical discretization of Schrödinger of second derivative, Cn is identically equal to 1 is a field, a standard second derivative. And let me tell you following. When in Soliton theory discrete system appeared, theory of total lattice, so-called, it was analog of Lux pair for it was discovered by the famous dynamical guy Henon, but inverse scattering construction was constructed by Flashka and Russian Monakov independently. But Lux pair was discovered by the famous dynamical guy Henon before them. So you need bigger family. You cannot construct this spectral symmetry within special subfamily used by classical numerical mathematicians. We can factorize this operator into product of first order difference operators, like that. But after permutation, Euler-Darboux-Backlund transformation will be out of that class. It does not exist within standard class. It is not compatible with complete integrability. By the way, for many physical problems in some models of quantum solid state phases immediately replaced, you started to use models borrowed from Soliton theory, where you need that. You need two fields in order to construct a completely integrable class of second order operator, preserving this Euler-Backlund Darboux type symmetry. Otherwise, it is not enough. It's interesting that symmetry Vn equal to 0 is compatible with complete integrability. It was used, but standard class not. Even so, in that case, two-dimensional operators are interesting. In case of quadrilateral lattice, I will show you picture in a minute. You have two shifts operator, two shifts. Shift in one variable, shift in another variable. And such operator is factorizable. All systems, discrete systems, which we heard here in our school, are associated with this operator on quadrilateral lattice, with this linear operator. And it is factorizable. You may do this exercise easy. In case of two-dimensional case, Laplace type factorization is simpler than one-dimensional. You don't need to solve Riccati equation. It's simpler. It's unique. That's so. Using gauge group like that, you immediately. Let me point out following. If you are working with standard discretization of second order Schrödinger operators, every point in quadrilateral lattice has 4 neighbors, so 5 points are involved. Point and 4 neighbors. These standard discretizations are not compatible with our discrete symmetry on the quadrilateral lattice. This operator is not elliptic, it is like hyperbolic. It is sum over vertices of elementary square. And standard discretization is not compatible with our theory. There are 2 lattices indeed. All classical difference theory was associated with quadrilateral lattice. Nobody worked with equilateral triangle lattice, except physicists sometimes in some cases when quadrilateral equilateral triangle lattices directly appeared from experiments like in superconductivity and so on appeared.
Are these operators skewed? Look.
Which operator?
On the previous slide.
Operators which I wrote are sum of shifts. It is second order difference operator it was.
Yeah, but that's what on the left hand side. But Q1 and Q2, are they low?
Q1 and Q2 are written here. It is simply something not far from difference derivative in one direction, yes. In quadrilateral lattice, you have few number of first order operators, like, so not much you can do. Not much you can do. The only operator which people found was some famous systems, like Hirota system, so on, associated in quadrilateral lattice, all operators, all integrable systems known to me are somehow always associated with operator which I demonstrated you before. A sum along vertices of elementary square with weights, where weights are coefficients of difference operator. For equilateral triangle lattice, indeed, it's much better. It's much better to have 6 neighbors for point than 4. And turns out that general elliptic real self-adjoint difference operator is always factorizable like in Laplace case. That's simple exercise which I observed about 10 years ago and just started to use that. Equilateral lattice is much better than it's not new. We shall see already in late 19th century, Poincaré tried to start topology with differential topology, completely failed, and finally turns out to simplicial complexes. Simplicial complexes, differential topology was constructed only 50 years later after Whitney, Pantriagin, and Tomlin's new era of ideas in differential topology. But Poincaré found simplicial complexes. It's important that equilateral triangle lattice is simplicial complex. Here, it has important family of first-order operators, and it is important for us. Let's give me Laplace-Beltrami operator on the equilateral triangle lattice is factorizable up to constant. That's corresponding operators, first-order operators, which can be used in order to factorize it, I call here black triangle operators. Let me just say a minute about that. What is black triangle operator? Just a minute. Okay, black triangle operator is written here. Just u, v, and w are some function coefficients. It is sum of 3 shifts. One might think geometrically that it is sum of values of functions with some proper weights along the vertices of triangle. Triangle is better than square. If you consider operator which is sum along the vertices of square, it is already second-order operator because 2 scales of length are involved, sides and diagonal. Triangles, simplicial complexes are much better. This theory might have also multidimensional extension. It is really first-order operators. In natural metric of simplicial complex, distance between all 3 vertices is same. In order to model something like Cauchy-Riemann operators, which is best possibility. Why it is black triangle operator and white triangle operator, let me explain you following. This is, there is natural coloring of equilateral triangle lattice, black and white colors. And if I write operator 1 plus T1 plus T2, sum of 3 vertices, it will just sum only along the vertices of black triangles, not white. Let me just point out to you, Krichiver and myself, somewhere about year 2000, made nice exercise. You see, consider trivalent tree, for example. A lot of people, especially in number theory, studied its theory of second-order operators in it, like Laplace-Beltrami. When number theorist tells you that we consider something p-adic, yes? So don't believe them, it simply means that they consider graph. Yes, p-adic means graph. Yes, you see. For p equal 2, you have p plus 1 equal to 3, so it is trivalent tree. Number of cycles they will call genus or something like that. But so that's, if 3 means no cycles. graph. Graphs are, in fact, there are big areas, analysis on graphs, that sometimes hide it under terminology of number theory, sometimes not, sometimes open the graphs. Yes, that's so. And turns out that second order operators in trivalent tree are not factorizable, no traces of integrability on it. And we just pointed out that fourth order operators has such Laplace type factorization, and constructed integrable system, just nice joke for fourth order operator means that second order ball is involved. Means that in second order operator is you have if just radius 1 ball is involved. Fourth order operator is second order ball is involved. Completely integrable systems appears. Now, one more idea is needed for complex analysis also. There are another important area where first order operators are important is so-called differentially geometrical connections or connections in theory of fiber bundles. The subject is elementary. If it would be so complicated as topologists write in their books written in terrible abstract language of birds, believe me, in that case, physicists like Young-Mills would never independently discover it. Yes, it is elementary subject which can be easily expressed in courses, undergraduate courses of ODE. The differential geometrical connections is simply overdetermined system of linear equations. If you can always solve equation in one direction, but if you have two directions, you have pair equations in one direction, linear equation, and in second directions. You cannot solve them. It is overdetermined system. The abstraction what comes to you, what makes obstacle to that, is what's called curvature. That's Young-Mills curvature, so on. That's, by the way, idea of Riemann was that curvature is always just non-commutativity of second derivatives in tensor analysis. It's also curvature is not just that something like some my friend thinks a curvature of that, but it is calculus. It is tensor calculus, non-commutativity of operators. So my discretization of differential geometrical connection is not coincide with standard discretization which is used after Kenneth Wilson, physicist, Nobel Prize winner, used for Young-Mills fields. It's different. But it works well for group GLN because I consider it as a theory of linear operators. Physicists needs compactly groups, and this choice of compactly groups is inconvenient in this approach, completely inconvenient. So it is overdetermined system of linear equations, which I call triangle equation. Following. Let me just consider only two-dimensional case, which I need. Consider triangulated surface with selected family of triangles called capital X and coefficients, non-zero coefficients, assigning for every triangle of that family and its vertex some number b, tb. You write this natural operator using this matrix element. It maps functions of vertices into functions of triangles of our family. We need following families. We need two-dimensional triangulated surfaces, manifolds, with black and white coloring of triangles, BW colored surfaces. There exists also multidimensional generalization of it. I call this, in two-dimensional case, discrete conformal structure. Just coloring of triangles into black and white colors with standard rules. If they attach to each other, they have opposite color. And there are two families, family of all black triangles, family of all white triangles. And equilateral triangle lattice certainly is, I would say, best example. There is also third family family of all triangles. In that case, if our family is family of all triangles, we call our picture discrete analog of differential geometrical connection. We don't work with any spaces of functions except functions of scalar functions of vertices. But we get all non-abelian curvature of Young-Mills type curvature, curvature of fiber bundle curvature fields. For the case if we have black and white color of triangles and all coefficients are equal to 1, black triangle operator, function which is annihilated by black triangle operator, we call discrete holomorphic functions. Our functions are purely real. This real class of real functions give us model of all complex analysis. If we have no multiplication, so it's what complex number is simply pair of real numbers. That's nothing else, yes? For special case of equilateral triangle lattice, you can write these operators as a simple this and adjoint operator. This is unitary operator shift, so adjoint operator to unitary is that. And it is, in this specific case, operator maps functions of vertices into itself, not into functions of black triangles. There is natural one-to-one correspondence between black triangles and vertices. It's important, so you can iterate this stuff. Let me just explain what is curvature. What is curvature? Curvature is following. Suppose you have family X of all triangles. This is that picture. And coefficients B non-zero, assigning number B to every triangle and its vertex. Suppose what is a curvature in the point P? Take value of our function in point P1 and P. Using triangle equation for that family of all triangles, you immediately find value in that point P2. Using point P and P2, you will find value in point P3. In P and P3, you find value in point P4, and so on. You are going around. Who told you that after full circle you are coming to unit operator? That's why it should be so. It is triangle matrix 2 by 2, in this case, two-dimensional case 2 by 2. If it is unit matrix, we are saying that curvature is 0 in given point. That's, but in principle, this triangle matrix has one eigenvalue equal to 1. Our eigenvalue is not clear, which non-zero, and also one non-zero upper triangle element, so it is 2 invariants. This also point of coloring. Ordinary geometric curvature, what I defined to you is a curvature of field. But ordinary geometric scalar curvature in two-dimensional case is simply number of edges or triangles entering vertex. Why? Good to write, for this number equal to 6, you have Euclidean geometry. If number is less than 6, you have positive curvature. If more than 6, is negative curvature. So this standard relationship between this number and scalar curvature should be something like 6 minus this number, a function of that, a monotonic function of that, yes? Besides that, I need black-white coloring, so therefore number of points entering every vertex is always even in my case. Let me just make following remark. Suppose all coefficients are equal to 1. Don't think that it is completely trivial case. No, not at all. Flat curvature in given points simply means that even number of triangles enters every vertex. It's even, so it means that it is equivalent to possibility to color every star of every vertex into black and white color. If curvature is flat in every point, so representation of holonomy representation, which I also can define it using so-called thick paths, maps fundamental group, in this special case into permutation group. And I require that it is globally flat connection. If my manifold is non-simply connected, I always can go to finite covering symmetry group. S3 has only 6 elements. So, but I am working with simply connected manifolds, so it is always flat. So I am dealing with flat connection. It is so certainly for equilateral lattice. The classical discretization of complex analysis, the discretization of analysis started in 1924, first time. It was not before. Difference calculus started before. Russian mathematician Lazarь Aronovich Lusternik discretized to the Laplace Beltrami operator and used it for some theorems about incontinuous limit 3 years before Hilbert School did it. It is acknowledged in modern literature. Lusternik is well-known mathematician. It's acknowledged that Lusternik was first who started difference calculus in 20th century mathematics. In 1940, French woman mathematician Lelong Ferrand, probably Lelong is her husband's name, invented discretization of complex analysis on quadrilateral square lattice. Her discrete analog of d bar is sum along the vertices of elementary square, 1i, I square, I cube, so on. But let me, and a lot of people used it, either rediscovered or developed her activity later. When I made talk in Paris last summer, people told me that they both are alive, she and her husband, and he still helps her to defend her priority rights. They're over 95 years old. So today's people live long, yes? Let me criticize this approach. First of all, this is already second order operator. It's not first order operator, because it is elementary square. As a corollary, factorization property is missing here. We are losing factorization property of Laplace Beltrami. Equilateral lattice is much better. A lot of people used this approach. My approach, which I developed with Vanya Vinnikov jointly a few years ago and continues to do this now, is based on equilateral lattice where factorization is possible. That factorization exists here. 6 numbers of neighbors is much better. In both approaches, holomorphic functions do not form ring in both. That's you forget about ring structure. For every 2 manifold with black and white triangulation, we defined discrete holomorphic function as real function satisfying 2 equations with black triangle operator is equal to 0. Let me point out that instead of constants, we, similar role plays the so-called covariant constant, such that both are annihilated by both black and white triangle operators. Of course, what is constant? D psi is equal to 0 and D bar psi is equal to 0, both. That's certainly. One of them is analog of D, another one is analog of D bar. That's certainly. No multiplication, so let me point out following identity, where MP is analog of scalar curvature. It's number of triangles entering every vertex. There are similar identities also in multidimensional Riemannian calculus. That's between square of some operators like Dirac and factorizable operators plays fundamental role. Indeed, in quantum theory, they also sometimes very important and people even associated supersymmetry property with them for higher spectrum. Factorizability property of operators is very fundamental. It played fundamental role in early numerical mathematicians. Analytical studies for one-dimensional Schrödinger plays fundamental role also sometimes if you are intent to solve completely some quantum mechanical problem as well. Associated also with supersymmetry and also with instanton calculus. Such identity exists. You cannot say that some theory is simply analog of complex theory of holomorphic functions without serious arguments. First of all, Liouville principle should be satisfied. Means if simple version is in compact manifold with conformal structure, which is simply black-white coloring, that every holomorphic function is should be constant. This immediately follows from the instanton trick. I don't believe that instanton trick was discovered first in just 1970s by Sasha Polyakov and others and used in famous works of topologists after Donaldson. It was used a lot in deep 19th century calculus associated with complex analysis, etc., theory, and so on, with linear version. That's very simple, so I have no time to go into details, but it is some proof is written how in zero modes of quadratic functionals associated with factorizable operators are satisfying to so-called self-duality equations, which is has twice less order than standard Euler-Lagrange equation. This is property of factorizable operators. Its nonlinear analog leads to discovery of instances in modern mathematical physics and topology. So, and proof that Liouville principle is given here on this board. Let me note. Now, let us just continuous limit. How to do continuous limit? We have to make some gauge transformation in order to make some one of covariant constant make ordinary constant. And after that, in continuous limit, 1/2 of the extend field to complex. After that, 1/2 of our theory goes to ordinary complex theory. Other 1/2 goes to nothing. To infinity. Maximum principle also should be true. Naive form of maximal principle is not true. But we prefer to that you cannot estimate value of function inside through the value of functions along the boundaries. But you have to consider function not as a function of point, which is real value, but as a function of black triangle, which is R2 value. For every black triangle, we have triple of values of function, which can be extended as a covariant constant. It is a point in R2. And for this, you can say that image of that of inner part always contains in the convex hull of image of boundary. That's the maximum for that. It's only illusion that I consider real valued function. They are real valued function of point, but as a function of black triangle, they are R2 valued. The maximal principle works. More as a last point, let me just tell you following point.
Can I just pick up the microphone again? I don't know how it's come off. So.
It is. Excuse me, I apologize. Now, crucial point. We have no multiplication. Can you define polynomials and rational functions or not? What is polynomials without multiplication? No multiplication, yes? That's, I told you that there are no multiplication. But you don't need multiplication to define polynomials. You don't need them. Polynomial is such function such that it is annihilated by k plus 1 times derivative, yes? Holomorphic polynomial means that it is holomorphic function, d bar of it is equal to 0, and it is polynomial if d applied k plus 1 times is equal to 0. In case of equilateral lattice, we always have, it is our discrete analog of d and d bar maps space of functions of vertices into itself, so we can iterate them. So no problem, define polynomials. So we have polynomials. Why not to have how to define Taylor series? Yes. Many years ago, I listened talk in mid-60s of my friend Yuri Manin. He spoke about some periodic valued functions of continuation of zeta function, and I was surprised that in discrete analysis, all series are convergent. Yes, I was surprised by that. So, but it is discrete geometry. Here, series are convergent, should be convergent. Also, that's so we have holomorphic polynomials. We have also right analog of ball. Analog of balls are following big triangles such that you have 2k plus 2 vertices, and they are black from inside. K equal to 0, k equal to 1, and so on. It is analog of balls in equilateral lattice. So you are losing round symmetry. You have only just Z-free symmetry. For every discrete holomorphic function, psi, and every big such triangle Tk, there exists and unique one holomorphic polynomial, discrete holomorphic polynomial of degree k, such that difference between them is identically equal to 0 with in all triangle T. You don't approximate it like with k derivative, like powers in the point. You approximate it by this function such that our function is identically equal to this holomorphic polynomial in discrete case in all this triangle. Now you have to construct Taylor composition. You have to take increased sequence of this black triangles Tk, analogs of ball, and so on, take this series. So that's everything is natural. And last point, which let me confess, oh my God, something is wrong. Why it does not work? I don't know. That's, of course, I should almost finish, so it is last point. I apologize, but it looks like something is, something does not work. Why I don't understand? I don't understand. Maybe something here. Cannot understand. Okay. Yes, yes. I can't understand what happened. Yes. Yes. So this is now Cauchy formula. Can you construct rational functions? Yes, rational functions. 1 divided by z. 1 divided by z, Cauchy kernel. It needs for two goals. First of all, to have boundary formula. And this I will demonstrate. It's easy to find some fundamental solutions can be found. 1 divided by z, if you apply Cauchy-Riemann operator to that, it is simply delta function, yes? So you don't need to learn Fourier's theory of abstract distribution in order to define delta functions for lattice, yes? It's equal to 1 or in this point and 0 otherwise, yes? So therefore, in mathematical courses, in continuous case, of course, proof will be the same, but it is allowed to do this only in courses of physics. What is Cauchy formula? You take fundamental solution of your Cauchy-Riemann operator. I can give you fundamental solution. I call it Pascal triangle, like that. 0 outside. 1 Pascal triangle means up to sign. So this Pascal numbers is going. This is fundamental solution. But looks like more hyperbolic. It is not analog of 1 divided by z. I can use it for Cauchy formula in following way. Take function bounded domain consisting of black triangles. Bounded domain. Take function which is discrete holomorphic inside. extend it psi. Extend it as a 0 outside. We call it psi tilde, extended function. Apply to this function psi tilde discrete analog of Cauchy-Riemann operator. It is, and you obviously have this formula because it is inverse operator. Yes, it is all proof. It is here. And this is in continuous case, what we do have is proportional to delta function of a boundary. In discrete case, it is located in this strip along the boundary. So it is almost like at best what we can, it's really boundary formula. Because outside of our domain it is 0, inside it is 0, it's only in the strip. But this is, just as a last point, is following. It was our stupid mistake of Vanya Denikov and myself. We thought that Fourier transform is divergent in this case, like in continuum case. I made stupid mistake. Believe me, all mistakes, even of important works which I saw in my life, in works of some famous people, after founding mistakes, we all were stupid. Yes, you simply can construct good kernel, Cauchy type kernel by Fourier transform, and it is convergent. And it has decay proportional to 1 divided by mod z, like that, up to non-isotropic, of course, but that's dominated. So, and it is unique. Unique function. Not, unique means two-dimensional real space, like that, like because unique up to complex multiplication should be. And this gives us really discrete analog of all rational functions. That's because you can apply d to 1 divided by z, it will be 1 divided by z squared, and so on. Rational functions, all these special functions do not need multiplication in complex analysis. And we constructed all of them in equilateral lattice. Let me just finish with that. I developed some theory concerning hyperbolic, Lobachevsky plane, of course, also. But in this case, this theory is much weaker. We don't have Fourier transform. We don't have analogs of polynomial. There are beautiful chaotic dynamical stuff here associated with problem even how to find boundary, what is boundary of ball in hyperbolic geometry. It is also complicated object, which in that case I solved this question. But my conjecture is still what I did not prove in hyperbolic case. Hyperbolic equilateral lattice is simple notion. It is simplicial complex, homeomorphic to two-dimensional plane, such that, for example, 8 number of triangles hit every vertex. But it is simplest version, 8. 8, 10, we need even number for coloring. But so 8 is best possibility. Equilateral triangle lattice in hyperbolic Lobachevsky plane is very natural object, but complicated. Lorentz group is much more complicated when it does not contain big abelian subgroup, no Fourier transform, no analog of polynomials. Natural conjecture in this case, which I did not prove, is that in hyperbolic plane, discrete, equilateral lattice, 8 meet, there exist bases of discrete holomorphic functions which are globally bounded, like in Poincaré model functions z to n. They are globally bounded on the unit circle. It's not like polynomials. And I cannot prove that. Numerical experiment is difficult, and I don't realize that, because boundary of ball will have, for ball of radius 10, will contain millions of points. That I calculated with corresponding exponential number is calculated. And that's so already so hard to make, I would say, numerical experiment without some non-trivial theory. Maybe some number theoretical stuff should be used. I don't know. But so this problem is big. So I did not resolve it. So but for Euclidean case, everything is very, very well constructed, as I presented to you. Thank you very much for your attention.
Are there any questions?
Yes. Thank you very much. I'm slightly confused about the last part regarding the connection of your Green's function with that of Roman Novikov and Grinevich.
No, Fourier transform. I did not discuss it a lot. It is very useful. It allows to prove, for example, standard type theorems that if you have functions with polynomial growth, in Euclidean case it should be polynomial. Yes, also that's all type. Yes.
So, in other
Yeah.
words, their construction, in some sense, is the correct
Just
analog of
Fourier
the-
transform.
and it's the correct analog of the D-bar formula.
Oh yeah, yes, of course. Its decay is like 1 divided by mod z, but non-isotropically with different coefficients in different directions. That's very good. It is that's of such a function which can simply write Fourier transform, and you will get such function. And you cannot construct it by hand geometrically because some strange numbers appears. How to find complicated algebraic numbers doing by hands this construction? It is really elliptic object
Understand?
because it's global, or even transcendent numbers appear. How to construct them just out of geometry? You will construct something what I presented to you, like Pascal triangle. This is trivial, yes? Easy, yes?
I understand. Thank you.
You understand? Hyperbolic construction is local. Elliptic construction is global. And in Lobachevsky case, in hyperbolic case, good equilateral lattices. I don't know whether yet, don't know enough whether number of theoretical people investigated them in the literature and so on, or which kind of representations might be used. It is not enough time passed for that. But nothing like Fourier transform exists here. It's no big abelian group. It is discretization of Lorentz group. Yes, it's no big abelian subgroup. No Fourier transform. It is where spaces, it's like groups where in famous works like Gelfand, Naimark, and Bargman started infinite dimensional representations. That's the big stuff, yes. That's complicated stuff. My knowledge of analysis, at least just for such short period, was not enough to develop it. It's very serious problem. How to construct special functions in case of hyperbolic geometry. Simply just triangulation such that 8 triangles hit every vertex. You can realize it geometrically in negative curvature, but you don't need to, you can use metric where length of every edge is equal to 1. That's,
Further questions? Then let's thank Professor